Alright, so we're finally ready to get our hands dirty and write some Rust. Now, what we're going to do first of all is we're going to discuss the data types that are used in Rust because, well, it's important. The programs, what they do most of the time is they store some form of data, and the simplest form of data that they store is numbers. So let me get rid of this line here, and we're going to try declaring some variables. Now, what is a variable exactly? Well, essentially what you're saying is you're saying that you want to allocate a chunk of memory for storing a particular value, like a number. So let's do a declaration. Let's take a look at what it's like. So I'm going to declare a variable called a, which is going to be of type u8, and it's going to have the value 123. Now, what does all of this mean? Well, first of all, the let part creates a binding. So we're essentially binding the variable which we refer to as a. It's a memory location that we refer to, and we bind it to the value 123, which means that we take a byte. In this case, the number 8 indicates 8 bits. So that's a single byte. We take a single byte and we put the value 123 in there, and we refer to this memory location using the name A. And this is great. Now, I need to explain a little bit what's happening in this part. So A is the name of the variable. We could have had a different variable like hello 123, for example. That's a valid identifier as well. I'm just keeping things simple here. Now the U8 is the bit that bears some explanation. So the letter U stands for unsigned. Essentially, when we talk about whole numbers that we want to store in the system, there are signed and unsigned numbers, and these are different. So an unsigned number is 0 or positive. So it cannot be negative. You cannot put a -1 into an unsigned number. It doesn't make sense. Whereas if I had an I here instead, that would be a signed number. So I stands for integer and U stands for unsigned integer. So as you can imagine, the range is a bit bigger. So if you have an unsigned single byte, that means its value can go from 0 to 255, whereas if the byte is signed, if I had an I in here, the range would be -127 to 128. So we're going to have an unsigned byte here. So the question is, well, what can you do with this value now that we've initialized it? So we have a variable called a. What we can do is we can try and print it to the console. Now, the way to do it is to use the println macro. I'm going to be using this macro a lot throughout this entire course, so you better get used to it. So this println macro, basically, I can specify what text I want to appear on the command line. So I want to have the value of a. So I'm going to say a is equal to, and then I'll put curly braces in here and finish the string. Now, what's happening? Essentially, this text, this part is going to go to the console as is. Nothing is going to change. But the curly braces are going to be replaced by the argument that comes after. So I'm going to put a comma here, and I'm going to add the value of a. So essentially, we're going to print a equals, and then take the value of a and print it instead of the curly braces. So as I run this program, you'll see that I have a equals 123. So it's very convenient to have this kind of notation. This macro is very useful. We're going to be using it a lot. Now, what is so special about the variable a? How is it different to other programming languages? Well, one of the problems you might hit if you work with this variable is when you try to change it. Let's say we want to give a new value. We want to change the value from 123 to 456. Now, as we try to compile it, you'll notice that we get an error, and it's all underlined in red here because we're attempting to reassign an immutable variable. So what is mutability? Well, with Rust, the variable bindings that you create are immutable by default, and by immutable we means that you cannot change the value. So as you specify the value in this format, you cannot change it afterwards. And if you want it to be changeable, you have to be explicit about it by using the mutable keyword, which is just a mut, M-U-T. So let's make a value which can actually be changed. So I'm going to have a mutable value called b, which is going to be a signed 8-bit integer, and I'm going to give it a value of 0. So now this thing is mutable. You can actually change the value. So first of all, let's print the value as is. So let's once again print the value of b. So b is equal to this value. But now what we can do, and this is in stark contrast to this, is we can actually change the value. We can say b is equal to 42, for example, and then we can take the print command and we can repeat it once again. So let's run it, and we can see that b is initially, it has the value of 0, but then I changed it. I actually managed to change the value, and it now has a value of 42. So this is great. This is what the mute keyword is for. If you don't have this keyword, you're not going to be able to change the value after you declare it. All right, so one of the things you can generally avoid in Rust in many cases is this bit, because the colon and the type, they basically specify how much memory the variable is going to take up. So the 8 basically means 8 bits. Now, you can get Rust to actually try and figure out what the type is without writing it yourself. So let me give you an example. Let's say I have let mute c equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, what we can do, I mean, you've probably guessed already that c is actually a 32-bit signed variable, 32-bit signed, which in Rust's terminology would have the type i32. So I stands for signed integer and 32 stands for how many bits it actually takes. But let's actually print it to the command line. So I'm going to do print line once again, and it's going to be a bit more interesting this time. I'm going to print the value of c. I'm going to say c is equal to this value, but then I also want to print its size, how many bits or how many bytes in this case the variable actually takes. So we know it is, I'm telling you that it's a 32-bit value, so it takes up 4 bytes because a single byte takes up 4 bits. So, but we're going to put it out. We're going to say size is equal to this many bytes. Right, so outputting c is easy. It's just c like this. But to find out the bytes, we're going to actually use a function. We're going to use a function from stdmem. So what I'm going to do up at the top of the file is I'm actually going to import stdmem, which is a namespace full of useful functions. And what we're going to do now is we're going to use that mem that we imported, that's operations on memory, and we're going to take the size of the value of c. And you'll notice that I have an ampersand in front of the c here. That's something that we're going to talk about later on. For now, just take it as is, that if you want to find out the size of the amount of memory that a variable takes, you call size of val and you put the ampersand in front of the c. So let's run this. And you can see that c has this value. That's the value that we specified, and the size is actually 4 bytes. So 4 bytes is 32 bits, just like we kind of predicted here. So everything is okay for now. Okay, so another data type, and as you can imagine, we have I8, U8, so signed and unsigned 8-bit ints. Then we have I16, U16 for the 16-bit, and then I32, U32, I64, U64. So these are the data types that you can actually use in your program. All right, by the way, notice that there is an underlining here. We declared something is mutable, but we are not actually changing it. So after you compile, you get these kind of hints that, by the way, you declared this is mutable, but you're not changing the variable. Incidentally, let's try changing the variable. Let's do something that will verify that the variable is in fact signed, because we know it's 32 bits, but how do we know it's signed? Well, if it's signed, then assigning a negative value to it shouldn't be a problem. So we can say c is equal to -1, and then I'm just going to copy this, but I'll say c is equal to this value after modification. So we're going to print c after we assign -1 to it. Now, if c was a unsigned value, then we would have a really crazy value, because -1 does not make sense for an unsigned value. But because C is signed, we can print it, and that gives us C equals -1. So we know it's a signed 32-bit value. Everything is okay here. Another data type that you can use is called iSize and usize. Let me show to you. Let Z equals, let Z of type iSize equals 1, 2, 3. So what is iSize and the corresponding usize? Well, these are integral data types which correspond to the size of the word, so the size of the pointer. Like if you had an address in memory, what would the size of that address be? Well, in the case of 32-bit systems, you would have a 32-bit variable. In the case of 64-bit systems, you'll have a 64-bit variable. So one of the things we can do is we can grab the value. Well, let's first of all grab the size of this variable that we have. So I'm going to have another let binding. I'm going to say let size of Z be equal to size of val, and we'll take the size of Z once again with an ampersand as before. And now we're going to print line a lot of things. So we're going to say that Z has this value. It takes up this many bytes. And then we can say that this is a so many bit operating system, because the size of the pointer determines whether you're in 32-bit or 64-bit. So the first argument, the first set of curly braces is Z. The second argument is size of Z. And the other argument is, because this is the number of bytes, we need to multiply by 8 to get the number of bits. So this is going to be size of Z multiplied by 8. All right, let's run this. Okay, so Z has the value of 123. It takes up 8 bytes, and yes, I am indeed running a 64-bit operating system. So this is useful when you need to have the variable whose size is the same as the size of a memory address on the system that you're running on. Okay, so these are some of the integral types. What other types are there? Well, there are actually loads. Like, for example, let's suppose you want to store a single letter. So I want to store the letter X. So I can say let D of type char. So in this case, it's a character, a single character, and we can assign it the letter X. So I'm taking the letter X and I'm assigning it to this variable. And by the way, this char thing is optional, because if I remove it, then the compiler will still figure out that this is a character, and it will still give D the appropriate size, just like it did when we had let mute C without the I32 on the right. So this is going to be just fine. However, there's a bit of a surprise. Let's actually, let's take this, and let's do it for D. I'm just going to change C to D here, and like this, and like this. Control 5 everything, and you'll see that D has the value of X, that's the letter X, but the size is not a single byte. It's not an ASCII or some custom encoding. It is in fact the largest Unicode set that you can have, so the size of a single character is actually 4 bytes, which might seem a bit excessive. Alright, we're going to talk about strings and text in a later section. Let's also talk about the non-whole numbers, because all of these, integers and certainly letters, they are stored in whole number types. Now, what about, let's say, the value 2.5, for example? That's not a whole number. So let's say let E equal 2.5, and once again, what we're going to do is we're going to print the value of E as well as the size, obviously. So let's run this, and you'll see that E has the value of 2.5 and the size is 8 bytes. So as it stands, the default behavior of when you write a value like 2.5, it becomes a double precision, let me just check it. So 8 bytes, double precision value. So it has 8 bytes or 64 bits, and its data type is actually F64. F stands for floating point. So I've omitted it here, but we could really specify it as F64. If I wanted to have a 32-bit value using 32-bit floats, I would have to specify it explicitly like this, E colon F32. In this case, if I run this, you'll see that it now only takes 4 bytes, which is 32 bits. So these are the two data types. They're IEEE 754 conformance, so everything is fine in this regard, and you can perform all sorts of operations on them. And the last thing that I want to mention is Boolean types. Now, Boolean variables, they represent two possible values, and those values are true and false. So this is a value which, instead of representing any of a number of values, it just takes two values. And the way you do it, the way you specify it, is very simple. You, for example, say let g equals false, and this now gives g the value false, and it's special. It's not as if we're encoding an integer to be 0 false 1 true. It does take a single byte, though, as you'll see in just a moment. So as I kind of output it, but notice that as I print it out, let's run this, it actually prints false. So g equals false, and it takes up a single byte. So Boolean values are very important because they are the result of a comparison. Like, for example, if you say let f equals 4 greater than 0, for example. Now we know that 4 is in fact greater than 0, so f has the value of true because the statement on the right appears to be correct. We'll talk more about comparisons when we go to operators, but that's it for the primitive types that Rust supports.